This lesson covers the application of Newton's laws. In this lesson, you will cover the following objective. Apply the ideas of vector mathematics and Newton's laws to solve static and dynamic problems. Newton's first law is the law of inertia, aka the law of balanced forces. A force is that which causes a change in motion of an object. In everyday life, we experience all kinds of forces. Often we refer to a force as a push or a pull. Newton's laws of forces says, first law, if no external force acts on an object, then an object at rest continues to remain at rest, and an object in motion continues to remain in motion at a constant velocity, i.e. constant speed in a straight line. Newton's second law is the law of unbalanced forces, which states the acceleration of a body is directly proportional to the force acting on it and is in the same direction. Here is an example. Suppose force, or F, acts on a body of mass, or m, to create acceleration, or a. Then, if force is doubled, so is the acceleration. Newton's third law is the law of interactions, aka equal and opposite reactions, which states, for every action there is an equal and opposite reaction, and the action and reaction forces act on opposite bodies. For example, when two objects of unequal masses, m1 and m2, collide with each other, the force on mass m1 due to mass m2 is equal and opposite to the force on mass m2 due to mass m1. F1 plus F2 equals this. The vector difference would be F1 minus F2. This means that all that you had learned about other vector quantities, for example, velocity and acceleration, is applicable to forces. They must be added and subtracted according to the rules of vector addition and subtraction. Review your previous instruction for more about vectors. This is the horizontal component of the vector and is found using the following trig function. This is the vertical component of the vector and is found using the following trig function. This is the process to get all vectors into what we call components. Components are perpendicular to each other. They would be the x and y motion if drawn separately rather than drawing the vector itself. Follow the process on the next series of pages. Let's look at single body problems. Given all the forces acting on the body, mass or m of the object, find the acceleration of the body. Or, given all but one of the forces acting on a body, acceleration of the body, and mass of the object, find the unknown force acting on the body. Step 1. Draw a free body diagram of the object. The free body diagram shows various forces acting on the body. The typical forces that you would include are weight, normal reaction, tension, and friction. There are two kinds of situations in which friction acts. When the object is at rest and is being pulled so that it cannot move, the force is called static friction. When the object is in motion, the frictional force is called kinetic friction. It always takes a large force to overcome friction when an object is at rest, rather than when it is in motion. In some problems, in addition to all the forces listed, you could also be given or asked to find an external force that is specifically applied in a given direction. Step 2. Draw the xy coordinate axis system. Typically, the x-axis is parallel to the surface along which the object moves. The y-axis is perpendicular to the surface along which the object moves. Review this image. Step 3. Find the angle between each force and the positive x-axis as shown in this problem. Calculate the x and y components of each force. This is the alpha and y components, where alpha is the generic angle which the generic force F makes with the positive x-axis. Step 5. Set up Newton's second law equations as shown here. Let's look at kinematics and forces on single bodies. Given mass of the object, all the forces acting on the object, all but one of the following kinematic quantities, initial and or final position, initial and or final velocity, and time. Find the unknown kinematic quantity. Or given mass of the object, all but one of the forces acting on the object, all of the following kinematic quantities, initial and or final position, initial and or final velocity, and time, find the unknown force on the object. You can use the problem-solving strategies to relate the acceleration of the object to other kinematic quantities, positions and velocities, or use the steps for relating the acceleration to the force. Let's look at multiple body problems. For each of the bodies involved, follow step 1 through step 5 in the previous problem type that relates to single bodies. Note the following. The coordinate systems of the two bodies need not be the same, i.e., it is possible to choose two completely different sets of x and y axes for each of the objects, as shown in the example. The acceleration of the two bodies is the same and can be denoted as the acceleration of the system, since they are both connected together or are touching each other as shown. If two bodies are connected with a rope or a rod, they experience an equal and opposite force of tension due to the rope or rod that connects them as shown. Solve the Newton's law equations for each body simultaneously to solve for the unknown quantities. Now go to your textbook and see if you can apply this information to your homework problem sets or any capstone exercises your instructor might have set up for you. In this lesson, you covered the following objective.